Yeah, now you can start.
Yeah, so thank you very much, Amit, for this opportunity and welcome everyone. So we are going to talk about quivers, which is just a directed graph. So especially we are going to talk about their representations. This is an extremely pretty subject. We are going to be seeing a very striking result at the end of the week, maybe even earlier. And the thing is that it uses only linear algebra. So I will try to go slowly. I cannot really help it because I'm a beginner in this subject myself. So I hope that I can justify the faith that the organizers have put in me. Anyway, please ask questions. Today's talk is really only about getting used to the basic terminology and thinking in terms that I will introduce. I also want to point out that the organizers have done an interesting and unusual thing in juxtaposing two topics here, which on the face are quite different from each other. One is quiver representations and one is Lie algebras. So, but you will see that in both of these topics, these very beautiful combinatorial gadgets called root systems will come up. And every budding mathematician should be aware that these things exist. And every budding algebraist should have at least a basic acquaintance with them. So, the root systems that will arise in complex semi-simple Lie algebras will take some work until you reach the point where they can be introduced. Unlike that in Quivers, Quivers is probably the setting in which it is quickest and simplest to see how these root systems come up. So you're in for a treat. Do persevere because there are lots and lots of rich rewards at the end of this. So references which I should list. So on the web page of this AIS, there are many references. So you can take a look at them. One of them, the most elementary one, is the book by Schiffler on quiver representation. So I will not list that. Uh, but I will write down a couple more references here. So there is a book by Ettinghoff and others, which is called, I think, an introduction to representation theory or something like that. It's a modern introduction, which does not just finite group representations, but also Lie algebras and quivers. It does several things at once. It's a fairly elementary book, uh, and it has a treatment of the main theorem that we are going to see. There is another one that I'm following, which is course notes by Henning Krause, and these are there on the archive, for example. Anyway, so what do we do today? We will of course see the basic definitions. That means what is a quiver, what is a representation of a quiver, and very importantly, what are morphisms between quivers, so that we have a category of representations of quivers, of a category of representation of a fixed quiver. Then we will see examples.
Sorry to
Representation,
disturb
yeah.
you. Just one question. Yeah, how would you like to take questions from the audience?
Yeah, so I would just, I'm happy either way. I'm happy for people to just blurt out questions. There is no problem.
Right.
If people feel shy about that, then they can just write in the, uh, in the chat section. But I will not be able to monitor the chat section. Then
Yeah,
somebody
we
can
will
just,
monitor. We
yeah,
will
then
monitor
somebody
the
can
chat
just jump
section.
in. And please
Yeah,
feel free
sure.
to, interrupt really anytime. Today, today really, I will prove, I would like to prove a couple of things because after all, this is a math workshop. But today it really is just scene setting. Right? So examples, some basic examples, uh, some basic examples, way to get new examples from old examples. So in particular, direct sums and simple modules. Yeah, so one other thing, we'll say quiver representations, but uh, fairly soon we will see that it, formally speaking, it is a special case of module theory for a particular algebra. So the language may fluctuate. Sometimes I may say representation, sometimes I may say module. Especially things like sub-representation or quotient representation is a mouthful. So you can just say submodule or quotient module. So simple representations. Etc. And why are we doing all of this? So questions and rules. So major point that we are going to see is Gabriel's theorem, whose outline at least we should be able to state today. And a major tool that we are going to use in order to do this is reflection functors. And a bunch of other things that will come along the way. And the last thing that I want to introduce is path algebra of a quiver. And we'll see examples of everything along the way. So what is a quiver? It's just a directed graph. So you can write down a formal definition, which you will find in all sources, and maybe I will also write down. But it's simplest just to write an example. So let's take something. So you have a bunch of vertices. And some arrows between them. So it's a directed graph. Let's say I can name these vertices 1, 2, 3, and 4. It is perfectly possible to have multiple arrows, multiple edges between the two vertices. It is also possible to have a loop at a vertex. So this is also allowed. This is allowed. This is allowed. Anything is really allowed. I mean, it's a graph. It's a directed graph. That's all. So nothing particularly exciting over here. What is more exciting is representations of a quiver. So formally, a quiver Q is Q naught, which equal to set of vertices. So in our example, this is 1, 2, 3, 4. Q1 is set of edges. So let's write down some names for these edges: alpha, beta, gamma, and let's say delta. And you can say that there are two maps, S and T, from Q1 to Q0. So what is this? It's just formal nonsense saying if I give you an edge, then what is the source of that edge and what is the target of that edge? So for example, in our situation, what we will have is that S of alpha is going to be 1 and T of alpha is going to be 2. Right? So I hope that this is completely straightforward. As always, if there are questions, please do ask. At this stage, if something is not clear, it is not your fault. It is my fault because everything, there is really nothing difficult so far. Okay, so it's just a language. So as I said, the interesting thing is not quivers, but their representations. So what is a representation of a quiver? Representation of a quiver Q. It's very simple. It's just an assignment representation of a quiver Q. Let's say V. It's just an assignment. Let's write this in words. A vector space Vi maybe subscript Vi. I think that's the standard notation, no? I. So in our example, this means that in order to have a representation of the quiver that I drew up there, you need to have 4 vector spaces that I'm going to call V1, V2, V3, and V4. And for us, they will always be finite dimensional. Okay, so first I should say fix a field K. If you like, you can take this field to be complex numbers or algebraically closed if you want to extract eigenvalues, because we are going to be doing linear algebra. But at the moment, I do not want to say anything. This is an arbitrary field. So that's what happens for each vertex. And for every arrow, what do? I just give a linear map. A linear map Vi to Vj for each edge I to j. So formally speaking, this will be some map called V sub alpha. Maybe if I call this edge alpha, then you can call this map itself V sub alpha. So V is an assignment. It carries a bunch of data, a vector space at every vertex, as well as a linear map between the respective vector spaces for each edge. Notice that for this delta that I have over here, this is
Can I
something.
suggest something?
Yes.
So age is usually undirectional. Yeah. Uh, I mean, it would
Okay.
be preferable to call it an arrow rather than
Okay,
an
so
edge.
let's
Yeah.
very good. So let's try to call it arrow. If I make a mistake, so remember I do not
No,
work
no,
alone.
it's
If
not a
I make a
mistake. It's
mistake,
not a mistake. It could be
yeah,
just a language
yeah. So
choice.
better terminology, correct. So I
Ah,
will try to stick to that. So for every arrow, there is going to be a map in the correct direction from between the respective vector spaces. So notice in particular for this delta, this is going to be an endomorphism of the vector space V1. Just an observation. All right. So let's go on. Still nothing particularly exciting. And one more piece of terminology let's introduce that for the dimension of V. Now, dimension of V is really uh, so what is a dimension? It's a bunch of vector spaces, right? So you could add the dimension, but what we really want to do is we want to keep track of what's happening at every vertex. So we call it a dimension vector of V is just the vector dimension of Vi I in Q0. So in our example, for instance, let's draw a representation right by the side of it. So if I say V1, V2, V3, V4, and some, then the dimension of vector of this will be D1, D2, D3, D4. Sorry, that it will simply be D1, D2, D3, D4, which are the respectively the dimensions of V1, V2, V3, and V4. Notice that the dimension vector is completely independent of the maps. It does not depend on the maps at all. Okay, so this is what we have. So the question is, why study this? I mean, after all, it's just some assignment, no, some decorated, some graph decorated with some vector spaces and linear maps. So what we will see is that studying these is really quote unquote just linear algebra, but it's kind of linear algebra on steroids. It's very highly, it's much more sophisticated than plain linear algebra, and we will see this today itself. A second reason is that studying quivers will give us a way to study general algebras. So algebras were defined by Shraddha, and we will review it shortly. But it will give us a way to study associative algebras in general. This is something that you will see later on this in lecture series. But the third reason is that there are unexpected connections between quiver representations and other parts of mathematics. One of these is this occurrence of root systems, which come up in many different places in mathematics. So all three reasons we will be justified in the course of these lectures. So let me reiterate that this is really part of mathematics that every young algebraist who's training now should know something about quivers. Okay, so an example of a quiver representation would be, instead of v1, v2, let us say let us suppose I have a two-dimensional vector space and a three-dimensional vector space here. Then this alpha, uh, the assignment of the linear map to the arrow alpha would be a map from a two-dimensional vector space to a three-dimensional vector space. So it will be encoded by a matrix of what size? Remember, it's a map from K2 to K3. So the column vectors are the images of the basis vectors. And so it will be a matrix of this shape, correct? And likewise, you can picture, if I have chosen an explicit basis for each one of the vector spaces v1, v2, v3, v4, then I will have matrices at uh, labeling every arrow. Okay, so I want to study these things. Let's try to look at the most basic examples that we can think of. And I will try to show why this is really linear algebra. We'll see linear algebra, familiar linear algebra, sort of in front of our eyes. So the very basic quivers, basic examples. So the simplest quivers that you can think of will have, okay, I mean, the most trivial one is just single vertex and no arrow. That has no interest. But a quiver with a single arrow. Now this can be of two types, where you have two vertices and a single arrow connecting one to the other, or a single vertex and a loop from the vertex to itself. Let's take a look at both of these examples closely. So this quiver, and a representation of this quiver will simply be a linear map from V to W, where V is associated with the first vertex and W to the second vertex. All right. And likewise, let's draw the second example where I have um, and so this means I will have a map from V to itself. So a square matrix. Now in linear algebra, linear algebra in some ways is really search for a good basis, right? We are given some linear map or linear maps, but certainly one linear map, and we look for a good basis to represent that linear map. Okay, so what is a good basis for V and a basis for W to represent some arbitrary linear map that is given to us? And this is something that we study in linear algebra right at the beginning when we do rank nullity, right? So what does it say? That I can choose a basis for V and I can choose a basis for W, such that the matrix of F takes what form, right? So we say that a matrix of, you will have some square identity block and everything else will be zeros. This is what I'm able to do. Yes. All right. Uh, so let's remember how this comes about. So what do I do? How do I prove this result? I'm just waiting for a minute for you to gather your thoughts to see how we prove this result. Right? Okay. So what we do is a standard argument is that you take the kernel of F or the null space. You take a basis of that, and okay. So you take the kernel of F, and on this kernel of F, how does the map behave? The map really is the F is just zero, right? That's what it means to take the kernel. Then what do? We take a basis for the kernel, and so the way I have written the matrix, this is actually the second part of the basis. So remember, so can't we just say we are applying row reduction and column reduction on F? Yeah, we can do row and column reduction, but I would prefer to have a slightly higher viewpoint. Okay. Because this is going to be useful. So what do we do? So the way I have written this matrix, the basis part, this is actually the part that I'm looking at over here, right? Okay. So after that, what do I do? Then I extend the basis, extend to a basis of Sorry, this is really terrible. Let me just say extend. And on this, I just I just apply F and I get the image of F, right? Now, what do I know about this restriction that I have written over here? This is a key part of the proof, right? Is that F in the extended part of the basis and to the image is this really is an isomorphism. This is a bijective map. After that, the tail of F as far as the domain is concerned is filled. There is nothing to do. But there is still part of W that I have not seen. That is the one that is left outside the image. So now I will say complete basis. This part is not seen by F. So the map is 0. All right. This is a very basic thing, and we are going to be needing this type of argument in more generality. All right. Okay. So having seen this, let's look at the second case, which is V with a single map. Now here you see the situation is more difficult because what I have to do is I had the in the first situation I had the ability to choose a basis of V and a basis of W independently. Whereas over here, uh, I have only a single vector space V, so I have to choose its basis once and for all. And you would have seen this, that this is a more difficult problem. But if your field is algebraically closed, then you know that a good basis is, for example, something that gives the Jordan form. Or you can use some other rational canonical form or whatever, right? So let's assume that the field is algebraically closed, K equal to K bar. And in that case, I can choose a basis such that I have in some basis, F is really just a direct sum of Jordan blocks. Okay. So already you see that a large part of linear algebra, certainly the first course that you see, is already captured in just these two very simple quivers. Okay. So in general, what we are going to see is that when you have a sort of bigger quiver, you really are looking at a configuration of various vector spaces along with maps between those vector spaces. For example, what you could have is that you could have a single vector space and you could have a bunch of subspaces of that. So let me just draw this somewhere else as a, uh, like for example, you could have a single vector space and you could have a bunch of maps coming in, and at sources of all of these arrows, you could put subspaces of this given vector space. So you could say that so that representation of this quiver is, among other things, a way of studying configurations of four subspaces of a vector space. All right. So this is the linear algebra part. Let's move on.
I just have a question.
Yes, go ahead, please.
Like in the representation, are you assuming that all the vector spaces are of finite dimension, or like we can relax that?
Right. So, okay. So I will make a definition, capital rep and small rep, when we come to the category. In practice, for us, we will always have finite dimensional representations, but you can conceive of infinite dimensional ones. In my definition, there was no requirement that it be finite dimensional.
Okay, okay, fine.
Okay, so this linear algebra, this search for good bases, is that something that we will codify this into a notion of isomorphism, and more generally into the notion of morphism of quiver representations. Right? So in all kinds of algebraic structures that you have seen, the structure itself is interesting, but the way to probe the structures and the way to understand those structures is to study the morphisms between them. So linear maps are much more important than vector spaces. We define vector spaces in order to study linear maps. And likewise, the way to study groups is to study homomorphisms between them, and generally like continuous maps for topological spaces, etc. So it is the morphisms that are more important. Before going to morphisms, let's just try to sort of formulate a very basic question that we would want to study for any kind of mathematical structure. We have defined quiver representations. Very first naive question is, you just tell me all of them. Can you find all of them for me? This is kind of like asking, well, can you tell me what all vector spaces are? And then you see, if I take, let's say, the three-dimensional vector space R3, uh, 3 slots. As a set, it's a different vector space than saying that I'm taking polynomials in with real coefficients in of degree up to 2 of the type a0 plus a1x plus a2 x square, right? I mean, it's a different set. However, as far as vector space structure is concerned, we regard both of them as quote unquote the same, right? In the sense that they're isomorphic. So somehow I need to have a notion of when to regard two different quivers as the same. And the notion of isomorphism is exactly as you would imagine. For vector spaces, the notion of isomorphism is precisely captured by dimension. Two vector spaces are isomorphic if and only if the cardinality of any basis for one of them is the same as the cardinality for the other. So let us see what happens for quivers. So the notion of an isomorphism for a quiver is going to be something like the following. Okay, so let's try to draw the same. Let's try to draw the same some representation like this for the same quiver, and try to imagine what it means for a representation to be isomorphic to that. So I have one. Imagine V1, V2, V3, V4. And I want to regard when such a thing is. So let me now just forget the loop for a moment. I'll just make one comment. Notice that the presence of loop made the search of base made the situation much more complicated, and this is the feature that is going to persist. We will at some point restrict to those quivers that do not have any directed cycle. So for example, if I remove this edge delta, then the resulting graph will have no directed cycle. Likewise, if I introduce an edge like this, then the graph now begins to have a directed cycle from 1 to 2 to 4 back to 1. However, if I reverse the orientation, then this is and I delete delta, then this is going to be an acyclic quiver for us, and we will focus on these uh, for much of our discussion. We will focus on these, but anyway, so back to the notion of isomorphism of representations. Okay. All right, so I have made 2 copies of this, and let's just do one thing. Let's call this W1, W2, W3, W4. So what should be an isomorphism? Well, it's the natural notion. You can imagine that there is compatibility between both of these, which is given by maps between the respective pairs of vector spaces, and of course such that everything that should commute does commute. So let's write this down. Isomorphism of quiver representations. Okay, so what do we need to have? Let's use a different color over here. How about, will this work? Oh, okay. All right, so let's draw. So that means that I need to have maps like this. So here is sorry about this. I should have really remembered to. So let's put this V4 over here, and let's put this W4 over here, and go back to our color. Okay. Right. So such that so if you can try to think of V1, V2, V3, and V4 in three-dimensional thing where they are on a horizontal plane, right? This picture over here, this picture is drawn on paper horizontally, and this picture is drawn on a paper underneath it. Okay, and all the mango colored arrows. So the reason why I just try to look for a color that starts with M for morphism. Okay, so some silly thing. Anyway, so imagine that the top V is sitting on a page and the W is sitting on a page underneath. Uh, so all of the black arrows are really horizontal, and all of the mango colored arrows they are vertical, right? So you are going to have so this is a square, correct? And what you want to see is that you want to have this square commute. So let's write this a bit more formally. So remember, since V is a representation, there is a V alpha, and likewise there is a W alpha. So what is an isomorphism of pure representations? It is a set of linear isomorphisms, let's say phi sub I from Vi to Wi. So I will have over here phi sub 1, and I will have phi sub 2, and likewise phi sub 3 and phi sub 4. Maybe those should also have been in color. And then the obvious squares should commute. So for example, going from V1 to W2 via V alpha and phi 2 should be really the same thing as going via phi 1, first doing phi 1 and W alpha. Okay. So this is what the definition of an isomorphism is. If you're bored, then I should ask you how I can apply this to write my first basic example over here in terms of some simple examples using what we did over here. And the same question over here. All right. So I hope the definition of isomorphism is clear. If there are any questions, then please ask me now. Okay, excellent. And so now I simply change the definition of isomorphism to the definition of morphism of queer representations. And instead of isomorphism, I will simply get linear maps. Linear maps such that I will simply say, is it okay to say vertical squares commute? I hope it's okay to say that in the lecture. You will, of course, be able to find the uh, appropriate definition in any text. So, for example, let's write this as, for example, if I first do V alpha and then I do phi 2, that should be the same thing as first doing phi 1 and then W alpha, etc. Okay, so good. Now we are in business. We have a notion of how to relate representation, two different representations, but remember of the same quiver. We are not changing the quiver just yet. Later on, we will see how to change quivers and do things with representations. Okay, so we get to say now that we get a category rep Q representations of Q. The field is not mentioned over here, but it is understood that there is some fixed field K. So small rep simply means I take the full subcategory. That means I just take the same morphisms as before, but I just insist that all my representations are finite dimensional. One thing which I forgot to say I think is that a quiver is a directed graph which for us will always be finite. And therefore, when I say that all the VIs are finite dimensional, it really is the same thing as saying that taken together also their direct sum, which I can sort of think of as an ambient space for the entire quiver representation, is finite dimensional. Right? So this is what the category of representations of a fixed quiver is. One of the goals of this, one of the subsidiary goals, if you will, of this series of lectures is to slowly introduce category theoretic language so that you can get more comfortable with this. So let's say some things about this category. If we say that Hom VW, and maybe I put Q over here, this is the set of all morphisms from V to W is a K vector space. There is really no mystery over here. If I take, so this is just some kind of version of many vector spaces somehow put together by means of some linear maps. No? So the notions that you have for individual vector spaces, many of them will just carry over. So how do I add two maps? I'll just do it pointwise. How do I scale a map? I do it pointwise. Because every square commutes for individual maps. So let's say I have phi and psi. Then every square commutes for phi and every square commutes for psi. Therefore, every square will commute if I take phi
हेलो
plus
आपने
psi.
कॉल किया था हेलो
Yes.
रिटर्न
I'm sorry. Is somebody
हाँ
trying to ask me something?
नहीं 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 वेट क्या है
I will mute the person. Yeah, just hold on.
हाँ सुश्रुत घोष नाम से सुश्रुत घोष आप चेक कीजिए
Yeah, please carry on.
Okay, all right. So, right. So morphisms from a K vector space, just by pointwise addition and scaling. And in this category, we have kernels, co-kernels, first isomorphism theorem. So what does that mean? If I have a V to W, which is phi. So you see, now I'm just writing it as if it's a vector space, right? Sorry. Okay. I'm writing it as if it's a vector space, but it really is understood that when I write this V, there is that entire graph sitting over there, and likewise for W. So if I gives representations kernel of phi. So what does that mean? That simply means that if you are thinking of this V and W as sitting on two pages, two pages that are held horizontal, then kernel is sitting, that is something on top of V1. So the kernel of phi1 will be a vector space over here. Let's say that will be K1, which will be a subspace of this. And likewise, you will have K2, K3, and K4. Representations kernel of phi, which is a okay, so I should even before this, I should have said that we have the notion of sub-representation, quotient representation. So if this is too many words at once, just hold on for a bit, because we are going to see examples of all of these things. And in tutorials, you will do hands-on calculations with these in examples. So what is a sub-representation? So for example, over here, if V is a sub-representation of W, that simply means that each one of the V's is a subspace of the respective W. Likewise, quotient means that each one of the W's is a quotient of the respective V. And I can take kernels. This kernel will be a sub-representation of V. The image will be a sub-representation of W. And I have the first isomorphism theorem. What does that mean? That means that if I take V mod kernel of phi, it is isomorphic by an induced map to. Come on, this should be straightforward. This is linear algebra. Wow, I think maybe it's too easy for everyone. So this is the same thing as image of phi, which is going to be a submodule of W. Nothing changes. It's all exactly the same. So we have direct sum of representations. And so what is the direct sum of representation? So V direct sum W I at a, so what does it mean to give a representation? It simply means I have to put a vector space at each vertex and a linear map for each arrow. So well, it's straightforward. Which vector space do I put at vertex I? I just take the two respective vector spaces and I add them. And if I have V direct sum W alpha. So this is, the notation may look a little funny, but this simply is saying that what is the map that I should put on the arrow alpha. And so this is really just V alpha direct sum W alpha, but you should actually understand what is going on over here. What this means is that for the arrow alpha, there was a map from VI to Vj, and for the arrow alpha, there is also a map from Wi to Wj. So what am I doing to these maps? Think of these maps as matrices. So this map is really the following. It is Vi, Wi and Vj, Wj. Think of the two bases as simply chained together one after the other. And the matrix over here is V alpha. The matrix over here is W alpha. And there are no cross components. I'm just taking a direct sum of two matrices just by putting them along a diagonal. So this is a block diagonal matrix. So this is the notion of a direct sum of representations. All right. So a lot of language. Let us see what we can do now. Yeah. Okay. So I got a little bit sidetracked in talking about all of the structure on this category. One way to put everything that I have written over here in sort of one term encapsulating is that representation of Q and rep Q are abelian categories. It really means exactly what I have said over here, that are abelian, and if you want abelian are k-linear abelian categories. Abelian category simply means that I have the set of morphisms between any two objects is an abelian group, and I have kernels and co-kernels, and the first isomorphism I have kernels, co-kernels, images, co-images if you want, and the first isomorphism theorem holds. I also need to have direct sum of representations. That's what makes an additive category, which is part of being an abelian category. And the k-linearity simply means that the morphisms have the structure of k vector spaces. But if you don't care about this language, you do not have to at this time.
Professor Kulkarni, can I just stop you for a moment?
Yes, please.
Yeah, so basically I wanted to gauge how many people know about this language. Like how many people knew about abelian categories before this? Can you please use a raise hand feature for this?
Let's take a look.
Yeah.
Okay,
Then
how
it will
many?
be easier for us to talk about it as we go along.
Right. But I do want to say that this is an extremely concrete subject. I mean, you should really think of this as just linear algebra, souped up linear
Yeah.
algebra. So if you don't know what an abelian category is, that is perfectly fine. Uh, you
Yeah.
should
There are
you should
25 people, it seems.
so but you should know how to take kernels of how to take a sub representation, how to calculate the kernel of a morphism, the image of a morphism. This works exactly like linear algebra. It's just working in at every single vertex. That's all. So nothing crazy is happening until now. Okay. So
May I ask, please?
yes, please go ahead.
Yeah, so isn't it a monoidal category? I mean, you can also take the tensor product, right?
Yes, but let's pass over it in silence. Complete
Okay,
silence
okay,
at the
sorry.
moment.
Okay, sorry. Okay.
Yeah, okay. So a little bit in two minds over here. Okay, let's come back to our question, the naive question that we asked. That is, given any kind of mathematical object, you want to just say classify all of them. Right? Sometimes there are very satisfying theorems of this type, right? For example, if you have a finite abelian group or a finitely generated module over a PID, you can just list them all and a very satisfying theorem. So we can ask a question. Now that we have the notion of an isomorphism, can we just classify all quivers, all quiver representations? Right? For a given quiver, can I just classify all representations? This is not as unreasonable as it might sound. For a quiver with a single dot and no arrows, this simply means linear algebra because all I have is a vector space. And I do know how to classify vector spaces. Vector spaces are classified by their dimension. Okay. So every vector space, if you want, is a direct sum of lines, one-dimensional vector spaces. So I can try to take this as a prototype for the type of theorem that I want to prove, okay, which is, I would like to say that, so fix a quiver. I would like to say every representation of this quiver is built out of some atomic blocks. And then it breaks up into two questions. What are the atomic blocks and how are they put together? So in case of vector spaces, we can say that the atomic blocks are just one-dimensional vector spaces, lines. And the way they are put together is by taking direct sum. That's exactly what a basis is. Okay. So can we do something like this?
So I have one more question, if you don't mind.
Please go ahead.
Yeah. So in the, I mean, whenever you have this category, I mean, maybe what the very first question comes to my mind is, can we understand the simple? Not asking that question, can we assume that this is not a completely reducible category?
Uh, I'm coming to that. No, so we still have not. We are still at a vague level. That is somehow looking
Okay.
for building blocks. Okay.
Sorry. Go ahead.
All
Please.
right.
Thanks.
So so how to interpret this? What are what qualifies as atomic blocks, and what does it mean to put things together? This can be interpreted in at least two different ways. And over here, I would like to simply state something which hopefully we will have time to just get to at the end, which is that this morphisms, etc., it may look like a lot, keeping track of many commuting squares, and it's may look like a lot. But there is one device by which I can at least abstractly think of this as a special case of a situation that we have already encountered. Namely, a representation of a quiver is really the same, can be regarded as the same as module over a certain algebra that we will define very shortly. And the word same as means equivalence of categories. But we do not have to become technical at the moment. For now, just with this thought in mind that somehow studying representation of a quiver is really studying modules over some algebra, right? That gives us a bunch of terms as well as questions to ask. So, for example, when I say that all of these things, sub-representation, quotient, direct sum, kernel, co-kernel, that language is already ready-made for modules. Right? I use that language for modules. So it's exactly the same. The When I see what the translation between the quiver representation and module over its associated path algebra is, these notions will just directly translate. But now coming to questions. For modules, I can ask modules over a ring. I can ask questions. What are its simple modules? Like building blocks can be understood in two different ways. One way is what are irreducible modules? That is modules that do not have any proper submodules other than 0. So these are called simple modules. And then we can say, well, how are these simple modules put together? So in case of in case where your ring is a field, the answer to these questions is again very easy. The simple modules are precisely one-dimensional vector spaces, and a general vector space is put together just by taking direct sum. In general, we are not so lucky. If you have seen representations of finite groups over, over, let's say, complex numbers, then one of these goes away, but the second property is valid. In that, you have to now classify what the irreducible representations are, but it is still true that a general representation is a direct sum of these. In case of quivers, what will happen is that the simple representations, at least in case of acyclic quivers, they are quite easy to understand. This is an exercise that we will get to in either today's or tomorrow's tutorial. So you will do this. However, direct the fact that everything can be, the hope that every representation is just a direct sum of simple ones is just hopelessly false. Okay, so that is not true. And so one has to, if one wants to have these kinds of building blocks, then what one has to do is also separately study the ways of putting different representations together. And this goes within the way to do this, the language to do this is homological algebra, some of which we will come to, some of which we will discuss. So extensions. All right, so this is one way of approaching the problem. That is, the atomic blocks are simple modules and ways to put together, hopefully direct sum, but if not, then try to study extension groups or do some homological algebra. A different approach is to say, well, I give priority to my desire that I want to have only direct sum decompositions. I want to have only those building blocks into which I can break up by direct sums. So notice I'm now going in a different direction compared to this last bullet point. In this last bullet point, I was given two representations and I put them together as a direct sum. Now I'm giving you a representation. Can you write it as direct sum of two representations? If we can, then I can say, okay, this is built up in a very simple way from two smaller things. And now I can try to keep going smaller and smaller and smaller until I cannot break up further. So the building blocks in this type of thinking are called indecomposable representations, or for rings, you call them indecomposable modules, modules that cannot be written as direct sum of two proper submodules. So this is going to be a key question for us.
There is one more question in the chat from Sadanand. Maybe we are quick with submodules. Restriction of V alpha should take the image of W1 into W2. Yeah, so something more has to be said, he's saying.
All right, so let's, okay, so in my definition, maybe I was cavalier.
No, I don't think you defined it explicitly. You said
Right.
we'll
So
look at examples
yeah.
later.
So right. Okay. So yeah. So you see, right. So when I say submodule in a sub-object in a category is also up to appropriate isomorphism. No. So okay. So just think of this as a submodule where all the phi's are inclusion maps.
Yeah, that's the point I was trying to make. It was
Okay,
just
fine.
be
But
quick.
yeah. But okay. So it's a so at the level at which we are talking, it's a technical point. Coming back to so questions. Classify simple representations easy for acyclic Q. Indecomposable representations. And this is a bloody hard problem. However, the main theorem that we will prove, and so on, right? So, and I will just say further. But at least say main theorem. We will see that. We will see. That is, in fact, you know what? Main theorem will list all Q for which only finitely many indecomposable representations. And the answer is these are ADE type Dinkin quivers. The details are not important, but there is already something amazing happening here. Lots of amazing things. Let me write down and then I will tell you. For these quivers, construct all indecomposable representations. Part of this you will actually be able to do, hopefully in the tutorial today itself, which is to say, so what are the features of this answer? So some amazing features are these ADE diagrams, which I will write down. They're all, they do not contain any cycles, right? Not only that, whether the fact that these quivers have only finitely many indecomposable representations does not depend on how you orient the arrows. For example, this is a type A quiver. The quiver that we saw earlier, the very first quiver that we had, this is called A2. And so this one will be called A4. Oops, okay. This one will be called A4. And this is called A3. But the amazing thing is that even if I change the orientation on some of these, for A2, if I change orientation, that's silly. It doesn't really change the picture. But for example, in A3, if I change this orientation and I put it like this, the fact that this quiver still has only finitely many indecomposable representations does not change. And likewise for everything else. And all the indecomposable representations we will be able to construct. And what will happen is that for each one of these, so indecomposable representation to dimension vector is a bijection. And moreover, dimension vectors are precisely positive roots in the corresponding root system. So remember earlier on I said that we are going to be meeting root systems. So for these quivers we'll be able to do So we'll be able to solve this question with, with great success after Gabriel. That is, construct all indecomposable representations explicitly using the using reflection functors and the while group. So this is going to be a highlight. One feature of these diagrams is that in none of them is they're all trees. That there are the underlying graphs themselves have no cycles, directed or not, doesn't really matter. So part of this result we will be able to prove either in today's or tomorrow's tutorial, which is that if a quiver has a cycle, directed or not, it doesn't matter. The moment that is to say, if the underlying graph of a quiver has a cycle, then it cannot have only finitely many indecomposable representations. So you will be able to construct an infinite family of indecomposable representations. This is really not very difficult. You simply have to remember our Jordan block example. Okay, so this is where this is where we are headed. So I said the main question that we are going to ask and the main theorem that we are going to prove. And so technical. So let me list the technical tools that we will learn along the way, which are very important. So one is reflection functors. Technical tools or technical terms, if you will. Root systems. And other things. So there will be a key quadratic form and so on. Later, some homological algebra, which is projective, injective objects in this category, maybe something about X, and a nice way to see where the quadratic form comes from. And let me list slowly increasing use of. So for example, so it was stated that you should know something about categories and functors. So here is a first exercise. If you don't know what adjoint functors are, then you should read what adjoint functors are. Not absolutely necessary, but it's a very useful thing. Okay, so this is really all by way of setup. Are there any questions? Because now we're ready to start work.
You meant functors.
Sorry, yeah, absolutely. Thank you. Adjoint functors.
Yeah, and I'd like to comment that one reason to study this indecomposables are these categories are Poole-Smith category.
Right. So this is this is a theorem that we are going to. Yeah, so this is a thank you for reminding. This is a theorem that we are going to use. But we will just black box it. Yes, that's on the agenda. So.
I have a question.
Yes.
So that result indecomposable representations are in bijection with the dimension vector. So is it like for any quivers or those Dynkin quivers only?
No. So for these.
Okay, fine.
For these quivers.
Okay.
So may I ask a quick
I
question?
don't understand. Like this dimension vector is associated to any representation, no? Like
the dimension
bijection
vector
is
is
with the roots.
associated to any representation. Okay, so yeah, so this is a badly written thing. So let me try to at least make it better. So of course, I'm not saying that for every possible dimension vector there is an indecomposable representation, right? What I'm saying is that if you take indecomposable representations, there are only finitely many, and whatever their dimension vectors are, the ones that do occur, they so dimensions vectors. Okay, and I hope that I have made this better now. in that the dimension vectors of indecomposable representations, which ones do occur, I will be able to read it off entirely from the root system, that they are precisely the positive roots. Okay, so I hope I clarified what I had said vaguely over here. Any other questions?
Yes, maybe we should
Yeah,
really
so I have.
apply it to Gabriel.
I'm sorry, say that again.
Yeah, the theorem is attributed to Gabriel. No?
Yes, exactly. This is Gabriel's theorem. Yes. And there are generalizations of this.
Yeah, so
Yes, go ahead, please.
okay. So you said that, okay, so suppose you have A3 type quivers, and you have directed all the arrows pointing from left to right. And you also said that if you change the direction of the arrow, then you don't get so still you have finitely many representation for that quiver. I'm wondering
Yes.
whether there is a connection between these two sets. For example, first all the arrows bit from left to right. Now you change some arrows, you get a new bunch of indecomposables. Are they related, or they are just random?
Okay. So, sorry, this is A3, A4. All right. So let me try to repeat the question, and then we'll try to make sense of it. That is, suppose I take, let's say, this orientation. I'll just write down. And let's say I change this one maybe.
Yeah.
Okay, so two different orientations. So if you want to say, are they related? I can ask you, well, in what way do you expect the relation? Because currently we have no way to relate representations of different quivers. Okay. But this is like this is a bad answer in the sense I'm just being pedantic, and I'm saying, well, this question doesn't have any precise meaning. However, later on you will see ways to go from one to the other. Maybe maybe Amit, do you want to say anything perhaps on this, or you'll say later?
No, I don't think I was paying attention to the question itself. I couldn't hear it properly.
So the question
Uh,
is,
uh-huh.
if I change the orientation, let's look at A4, and I have written two
Uh-huh.
orientations over here. Now the theorem
Uh-huh.
says that the indecomposable representations, their dimension vectors are actually the same.
Right.
Because, right. So the question was, is
Yes.
there any kind of connection between indecomposable representations of one versus indecomposable representations of the other when the orientation changes? So my first sort of
Right.
bad answer
Uh-huh.
was that right now we don't even have a way to make sense of how to relate. But there is a better answer. Do you
Right.
want to say anything at the?
Yeah, I mean, you will see more like a better answer in the third week. Yeah, in the next week, I will show you something called the Auslander Item quiver, where all these indecomposable representations are themselves vertices, and then some maps between them are taken. And then for different orientations, you will have different Auslander Item quivers. And there is something called tilting theory. Yeah, so tilting theory will correspond to different orientations of the same underlying quiver, underlying graph, and you can go from one to another. Yeah, you can translate them from one to another. Like,
So there is a
yeah.
way, it looks like. Thanks. Okay.
Yes, there is a way. Yes.
And so let me just add to that there is a different way also, which we will see, which is maybe simpler. Uh, at least at least I know it, whereas the what Amit said I do not know. So when we see these reflection functors, what they do is that they appropriately change orientations of some arrows and give me representation of a new quiver starting with representation of the old quiver. And in proving the theorem, this is going to be a key thing for us, how these reflection functors behave on indecomposable representations is going to be an extremely key consideration. So we will see this happening in specific ways.
All right.
All right. Anything else?
Maybe one comment on the same line.
Yes, go ahead, please.
Yeah, so the notion of mutations are not yet there, but the two quivers seem to be mutation equivalent. So one can, like
Yeah,
the tilting objects are
right.
same.
But I mean, what is mutation? No, we don't have anything like that.
Yes.
Right? So,
Yes.
okay, so let's get to it. So let's start work. So there are two different things that I want to do today. Let's look at simple modules. So some simple modules. For a given and this is the so given a vertex I of Q, define SI. Now notice this S round bracket I. Okay, so this entire thing is a representation by SII to be K, SI J to be 0 for all J not equal to I, all maps 0. After all, I mean, I'm allowed to put any vector space at each vertex, right, that I want. So this is what I choose to do. I just put the 0 vector space everywhere except at one chosen vertex I. And over there, I just put a single line so that K is K1 if you want. And all the maps are 0. All right. So if there are no loops, then all the maps are forced to be 0. You see, because K can participate in the map only with 0. But what I am saying is that even if there is a loop from K to K, that vertex I to itself, even that map is 0. All the maps are 0. Okay. Now, just take a moment to see that this module is simple. You don't have to do any work, because if I have a submodule, then at every vertex I have to take a submodule, right? At other vertices there is 0, there is nothing to take. So there is only one vertex where I can go smaller, but I have put a line. The only proper submodule is 0. So this is obviously simple. So clearly, words like clear and obvious should be used judiciously, if at all. But I think in this particular case, we are okay. So clearly, SI is simple. And now, the claim Q is acyclic, then the SI are the only See, I have already switched to the language, simple modules. What I mean is simple representation or irreducible representation. Also, a very easy point. All of these SIs are pairwise non-isomorphic because they just live on different vertices, correct? If two representations are isomorphic, according to this, picture that I wrote down, every phi is an isomorphism in that case, a linear isomorphism. In particular, the dimension vectors have to be the same. The dimension of V1 and W1 has to be the same because phi1 is a linear isomorphism. Okay, so so the proof of this is something that I'm going to leave as an exercise for the tutorial. But let's make some relevant noises over here. Okay, so relevant. So here is the key question. No, key question. Given, so suppose I give you a simple module, right? So simple module, let us say V. This V is supposed to be one of the SIs. That means for this V, somehow I should be able to locate a magic vertex. How am I going to look at this V, which could potentially be in many different places, and somehow pick a magic vertex out of that? This is the thing that we have to solve. So here is a relevant thing. So some useful facts about, or let me say, observe. Some observations. Every acyclic quiver has a source and a sink. So what does a source mean? It means that every single arrow every single arrow in which this vertex participates points outward. There are no inward arrows. Can a vertex be both a source and a sink? This is just a question to see if you are awake. The only way a vertex can be both a source and a sink is that if there are no edges whatsoever. So it's just an isolated lonely vertex. All right. And so far, we haven't really said this, but maybe we will go back and say this earlier, that generally we will take connected quivers. That is, the underlying graph is connected. Quiver. Finite directed graph. So notice that connected over here does not mean that from every vertex to every vertex there should be a path using the given arrows. It simply means that the underlying graph is connected. That is, if I forget all the arrows, then it does not break into components. Okay. So is this observation okay? Just take a minute. Okay. So how am I going to find a sink? Well, just take any vertex. If it is not a sink, then what does it mean? That it will have an outgoing arrow. All right. Walk along that arrow. Can you come back to the same? Can you come back to the same vertex? The answer is no, because I said that my quiver is acyclic, which means to say that there are no directed cycles, so I cannot have loops. Okay, so I started. So let's just give some names. So I started vertex Z. If I started vertex V0, I started vertex V0. No, yeah, okay, V0, or maybe I0. I don't know. If it is not a sink, then that means there is something outgoing. So I will get to another vertex. Let's call it I1. If that is a sink, I'm done. Otherwise, something outgoing will be there, and that will go to I2. I cannot ever come back to any vertex that I have already visited, you see, because that will create a directed cycle. And my underlying graph is always finite. That means that at some point I must just get stuck, because I can never visit a vertex that was already visited. That would create a directed cycle. And I have only finitely many vertices to visit. That means at some point I'm going to get stuck. I cannot go out of it. So that means that this vertex has to be a sink. And now you just run this argument in the opposite direction, and then you will get a source. That is, keep walking backwards. Anyway, so this is one thing. I would like to do another simple calculation over here. Let us look at let us look at so decomposing, so understanding A2. I mean, we already understood it. No, it was just linear algebra. Remember what A2 is? It is simply a single arrow connecting two vertices. So this is what we did over here. Let's now look at this again carefully, right? So what this is saying is that I can break this map F into three completely different parts that do not talk to each other at all. Take a basis for the kernel. Now let us call the span of that to be V1. Okay. Or maybe V1 is bad because let's call this V prime. Everything in V prime is going to 0 under the map F. Now, when I extend the basis of the kernel, the span of the remaining vectors I'm going to call V double prime. When F maps by means of V double prime, I know that it maps isomorphically. So the image of that I'm going to call W double prime. And when I complete a basis of W by starting with a basis of W double prime and adding something, I'm going to call that, I'm going to call the remaining part to be W prime. Okay. So with this in mind, what have I done? What I have done is that this representation, the one that I wrote over here, this representation, I have broken it up as a direct sum of three representations. Let's write those down. Okay, so keep this picture in mind, please. Understanding A2. So V to WF is isomorphic to the direct sum of what? From V1, I have the 0 map to 0. Sorry, not V1. I had V prime. Then I can just get this right. V double prime to W double prime. I had F, restriction of if you want, and this was an isomorphism. And then I had a map from A. So you see, this really is a direct sum of these three representations. That earlier identity that I had and the zeros, I can really instead think of this as, you know what? I'm a bit in two minds over here. Let's do the following. Let's change. Remember, this F is an isomorphism. So I can change the basis of W double prime to be from whatever basis I took off the image. I can simply take a basis of V double prime and I can say with basis F of basis of V double prime. And if that is the case, the matrix of F with respect to that basis simply becomes the identity matrix. You see? Just think about it for a moment. This is exactly what it means to write the matrix of a linear map with respect to a basis, right? I'm saying, so if I have F of V1, some vector V1, and then it is F of V1. So when I write down which I'm taking as a basis vector, so in terms of the chosen basis, this really is the column vector 1 followed by zeros. Okay. So what we said is that thus the let's call this thus given representation of A2 is isomorphic to a direct sum of three representations, and the first representation is k going to 0 taken dimension of v prime times. The last one is going to be 0 going to k taken dimension of w prime times, and the middle one is going to be just an isomorphism, right? So this is just k going to k by equality, the identity map, taken as many times as the dimension of v double prime, which is the same as the dimension of w double prime. So you see, I was able to just using linear algebra, nothing else, I was able to write down any given representation of A2 as a direct sum of 3 different types of representations. Okay. Any questions so far? What we are doing is extremely basic, but you have to understand this. Because if you do not understand this, then things may become, we are just going to do more things of this type later on. So if there are any questions, then you do have to stop me and ask now. Okay, very good.
How to see this k to k is not a simple? I mean, take a one copy.
I never said anything like that. I am simply saying this is a way I have written it as a direct sum of 3 different types of models. Now let us understand. Now let us understand the question. Now let us address the question that you're asking. So there are 3 different kinds of representations that I got, right? So note 3 kinds of representations. 0 to k, k to k, by where the map is identity. So I'm just going to write equal to, and the last one is k to 0. Which is just identity, and the last one is k to 0. Okay, so I can think of, so what did I do? In some ways I answered a question, the second type of decomposition I'm looking for, that is given any representation of this easy quiver A2. I show that everything can be written as direct sum of these 3 different kinds of representations. Now look at, now let's just call these vertices V1 and 2. So this one is really the same thing as the simple representation at 2. And this one is simple representation at 1. Okay. Now, with the result that I asked you to prove and believe for now, those are the only simple ones. See, this is an acyclic quiver. That means the representation here in the middle is not simple. And we will be able to see this in a moment. There are 2 things to observe. One is that this is not a simple representation. But 2, this is an indecomposable representation. You cannot write this as direct sum of. So this one is not indecomposable, not simple. All right, so let us see that this representation is not simple. Okay, so that means that it should have a sub-representation. Okay, this sub-representation must have a dimension vector. I think I have a, okay, I'll just really finish in a minute. This sub-representation must have a dimension vector. That dimension vector, because the total dimension of what I am trying to find a submodule of is 2, any possible sub-representation can have dimension only 1, total dimension, that put together both vertices. So the only possibility that I have is 0k or k0, right? So you see, the only possible sub-representations are really the ones that are listed over here. The top one is a sub-representation because I will be able to construct an injective map. All right. So this map, which map is this? I do not need to ask. Any map from 0 is 0. And you know what? Let's go back to, go back to our mango color. This is the 0 map. This map needs to be injective. Remember, I want it to be a sub-representation. So there is really no choice. It has to be the whole, all of K, just inclusion. It is crucial to see that this is a sub-representation. Let's do this another way. Is this bottom one a sub-representation? Let's check. There is again only one possibility, which is I have to define maps where this one will be inclusion and this one will be the zero map. What I have over here, is it a sub-representation? Is it a valid representation map? And notice that it is not. Simply because if I go this way, the vertical map is an inclusion, so it really is identity, as is the horizontal map. So I should get identity. But if I go this way, I'm passing through a zero. So that's the zero map. So this bottom one does not work. However, the top one does work because notice any map originating from zero will always commute, no matter which way you go. Different maps originating from zero, they're all zero. Likewise, any map ending in zero will also commute. If you have different maps ending in zero, they will all be zero maps. So this one, the top one, is a valid submodule. And what you see is that the bottom one is not a submodule. However, it is a quotient module. So you have a map this way and you have a map this way. Let's just quickly check. The diagram that I have to see whether it commutes, it goes from this K to this zero. So of course, all maps have to be zero, but just check. You go from K to identity to itself, but then it goes to zero. Here to identity to zero. So what you have over here is that this middle guy, it is not simple. It has an exact sequence, a short exact, or if you want, this is a submodule. S2 is a submodule. S1 is a quotient module. But we just saw that this sequence is not split. There is no direct sum. Because if you want a split sequence, then this bottom one, this surjection has to split. But we just saw that there is no way to split this. So what you have is that this is an indecomposable but not simple module. A very easy example, but you do have to understand it properly. In the afternoon, we will try to play the same game, but now with A3. Okay, so we did not get to the path algebra, but it is okay. It's